你说好，这个笔不对 ，it's not right. It's not right pen, not pen. So if you look at this matrix there, let us just ignore some of the matrices. If you look at that I call M plus MC. This is MC. This is MC, and this is MC. And now if I sub those in there, this is W double dot, and this is W double dot C minus W double dot plus, forget about this data, okay? Now, you can have a data there. 0, 0, 0, 0, C, and this coordinate system just becomes like that. WC dot minus W dot plus K0 and KC0, and this is W and WC minus W, and then we are equal to this equal to minus M M minus MC, then times AG. Okay. That just means that there's no couple between W dot and these terms. No coupling between W dot and WC dot minus W dot, and no coupling between W and WC minus W. But there's a coupling between W double dot and WC double dot minus W double dot. So that's what it means. That means this is not 0, this is not 0, so that we have we are coupling between this and that one. Okay, that's just a coordinate. This is just a coordinate. If we change the coordinate, then your matrices will be changed. That's just a message I try to give to you. So I designed this homework for you to understand this kind of coordinate transformations. The second one, the 5B. The 5B, that's it's all the 5B and 5A. If you look at 5B, and if you look at 5B, and then you will see that 5B and 5A, they are the same system, except now I wanted you to design a active control system so that will mimic the right hand side TMD, and the right hand side TMD, the dynamics equations already shown in the last slide. That's there, right? Okay. Any questions you have? Any questions?
AG.
AG. AG. That's AG is the accelerations of the ground. 地的加速. So when you have an earthquake, then you have the age, you have accelerations of the ground.
这个方向.
Wrong, either directions. Okay, you go this direction or that direction. I go that direction is positive. The other direction is negative. So AG is just your ground accelerations due to the earthquake. Well, just like the earthquake yesterday, right? The earthquake will shake the 101. If you look at the TV, they show you the 86th floor. The TMD is moving. Yeah, it's moving. What they say 15 centimeter. Yeah, 15 centimeter. The displacement, the mass, the total mass moves about 15 centimeter. So that helps. So that's what it means. So this is good. That means we give you one-on-one the earthquake simulation, just like yesterday earthquake, and that's what you got there. All right. Okay. Now, if you don't have any questions, then I'm going back to the my ABA lecture today. Let's go back to my ABA lecture. All right. ABA lectures. That's 101. Okay. This is I modify the file. I demodify the file for this set of slides, so you can download it from our website. If you do that, because I add about 2 slides in there to explain better for the concept. Okay, now this is PDF or this PPT?
这是 PPT。
PPT. Okay. Then we need to move. Wait a second. Just wait a second. We need to move to how do we move now? We need to move to I think we done the displacement. We need to go through a second, right? The PDT we talk about dynamics. Okay, so we finish this guy. Now how can I go? How can I go to exploit here? 看到啊？
这样他们可能会看不到。
哦，看到 ，OK。那就是把它换回来吧。碰到了，看到了那个了。
这样可以。
没事的。还可以，所以你是这样放的，不对吧？
没有那个。
Okay, all right. Let us review a little bit of the last week. Then see I add a little bit more clear. The when I get measurement from my sensor, and that measurement, the W measurement, will go to that locations in my dynamics equations. That means on the right hand side. That means go to this right hand side equations to allow this computer to integrate these dynamics equations. So because WC, all quantity with sub C, those are the computer quantities. Those are not physical quantities. So those are the quantity computer generate. So what the computer needed is the measurement from these sensors. So we just give this measurement to these equations, and then the computer will be able to integrate these equations to get W and WC and WC dot. So when computer get this WC and WC dot, then they will get the call. They will get what? They will get the W. The W will go to this this quantity so that we can have the U term. This is the U term. This U term is the term U given by the model. And so this is supposed to be. Why can't I have UC here? I think this is supposed to be U. This is not UC. This should be the U. The feedback force generated by the model is called U, and U equal to minus Kc This KC is given by the computer, and W is given by the sensor. W is given by the sensor, and WC is given by the computer. All right. So this is much more clear than the page before I add the 3 arrows, right? So for you to understand how computer works and how they generate the U, so as soon as you get a W measurement from your sensors, you give that to the computer, and computer integrate this one, and they create a U. And they will generate U to get the feedback force, and that U is computed by minus KC parentheses W from measurement minus WC from these integrations. Make sense? You think? All right. So this is what we call the feedback, the dynamics feedback, and this dynamics really given by the computer itself. So it's not real dynamics; it's the computer computed dynamics. Okay? All right. Shim is okay, right? All right. So this is the last one is really mimic to this system. This is the last one is mimic to this system, and this system, this is the system they mimic. So we need only displacement measurement to go to the system and to go to the computer. This is the computer. All right. So that that's the mimic system for the feedback control. For this kind of mimic system, if you look at this, then the closed loop system. The closed loop system means we put feedback into the dynamics, and then we got a closed loop system. That means we put these 2 equations into a matrix form, and that's the matrix form. And this matrix form, we have the M00MC, W dot, double dot, WC double dot, and we have the damping term matrix, the 000C, because we assume the system has no damping there. And then we have the K matrix, that's K plus KC minus KC, and the minus KC K, and W dot WC dot. That means after we mimic this system, the closed loop system can be written in this way. This is 0, because we put all the U side, all this U side to the left hand side, all this U side to the left hand side, and then we write in terms of this closed loop system matrices. You gotta learn how to do the closed loop system. And by the way, you can download this file from the website. All right. And when you do homework 5B, you need to get this closed loop system, a matrix, but this not this form. I will tell you what kind of form you will get, but this not this form, because this is for displacement. The homework is for acceleration. So this is for displacement, but the form will be like this, and we'll talk about that later. Now, if you look at this, for this displacement measurement only, the coupling in the closed loop system, the coupling is in the K matrix. The coupling is in the K matrix. And there's no coupling in the mass matrix. There's no coupling in the damping matrix. They couple through only the stiffness matrix. Any questions? This equation is nothing but just write out this and that and put in this form. That's all. Okay. Any questions? Wait, where's the problem? Here? Oh yeah, there's no dot here. Sorry. No dot here. No dot here. Okay, that's good. Yeah, because I just did it yesterday. All right.
Because why this other one is the damping model is not symmetric.
The damping is symmetric matrix. We have a diagonal term. This 0, 0, 0 still symmetric, right? Agree? Yes, right. So the diagonal term, it can be any value. The off diagonal term, then they are symmetric matrix. All right. So this is I will change that. This the no w dot here, no dot. This is a computer fault, right? It's easy to copy and paste. So I just copy and paste it, but without changing the dot. Sorry, no, that's true.
老师，什么情况下不会 symmetric？
Oh, the student ask some under what condition they are not symmetric. For any passive system, it must be symmetric. But for active, like my homework number 4B, the active, that's not symmetric. So active matrix, active feedback doesn't mean they are symmetric. No. That means there are no passive system you can mimic. If your feedback system, your feedback, and then you write it into a closed loop system and matrices, and if you find out they are not symmetric, that means there's no passive system which you can mimic. So feedback system has some disadvantages. That means because they may not be symmetric. If they may not be symmetric, means they may not be stable. They may be stable. They may not be unstable. They may not be stable, or they may be stable. There's no guarantee. But the passive TMD, they guarantee they are stable. Cannot be unstable. But that's the natural law. That's a Newton law. It cannot be. The TMD like a 101, the TMD in 101 cannot be unstable. So it helps. Yesterday just was weak. So it helped. All right. This is for displacement measurement only. In next, this I added the new one. This one here. Okay, this W dot also not right. The closed loop. This one need displacement and velocity measurements. All right. Now, what is the differences? If you look at this chart and last chart, last slide. Look at last slide. On this slide, did you find any difference? The difference is I move the despot from the right-hand side, touch to the ground, to the left-hand side. If you look at carefully, last one, this one here, the despot is touched to the ground, and this one is not. This one, I move the despot from that side, from right-hand side to the left-hand side, without touching the ground. If you write the Newton law, and this is nothing but the Newton law, and system and virtual system, that's the Newton law. You write a Newton law out, then you find out you need not only the displacement measurement, also you need velocity measurement. So from here, we have W dot on the right-hand side of U, we have W and W dot on the right-hand side of U, right? You see that? So you cannot move, if you want to mimic a system, you cannot move, say, from this one to that one, and using the same equation of motions. When you move the device from one side to another side, you got to be careful. You understand now? Because when you compute this U, I need not only W, I need also W dot. because W and W dot are required for this U to be computed. See this U there? This is follow Newton law. Kc is W minus Wc, and this eta C, W dot minus W dot C. Another one the same thing. So that is displacement, that's the velocities. Wc, we don't worry about it. Wc is computer quantities, that's computer generated. It's not from measurement. It's not physical quantity. All the quantity with sub C are not physical quantities. They are virtual quantity. They are not real one. They are imaginary one. But all the W without C, they are the physical quantity. If you need that quantity to compute your input, your U, then you need the measurement. Agree? Okay. Now, if you still puzzle about it, we go back to that slide. You will see that this one, U, there's no dot, W dot there. This one, there's no, minus U, there's no W dot there, right? They do have WC dot there, but WC dot is not physical quantity. You don't measure it. That's, you compute it from your computer. Any questions? Any questions? All right, so you've moved this device from this right-hand side, that device touches the ground, to the left-hand side, then you need one more measurement. That's velocity measurement. And for that, you also have the this coupling in W dot. You have this coupling in W. So this is not W dot, it's W. Any questions? So clear enough, right? So when you want to mimic a passive system, you got to be very careful where your device is put. By the way, this is mimic system because it's a zeta C. So it doesn't matter it's put in this side or that side. As a matter of fact, that's true. It doesn't matter because that's my computer quantity. The zeta C is my quantity. So for this equation, it doesn't make any sense for this, because if you have only displacement, your mimic system is the one in last slide. Then I will show you the same thing here that you can change it to. You can do something else. You can use the acceleration measurement to do this kind of figures. All right. That is the for multiple degree of freedom. I'm not going to talk about it. I'm going to skip this. All right. This is quite theoretical derivations. So I'm going to just skip that. So I'm going to talk about the that's the one I skip it is just only the multiple degree freedoms. So it's not. Let us okay. Let us look at the. Okay, let's look at this. Okay. Yeah. Let me just explain this one a little bit more. All right. If you look at these equations, that's the equation we mimic for the dynamics of a virtual passive controller. And how you do this? When I mimic system, I just write the passive control first, like this. I write this closed loop system first. And then what I would do is I move that. All right, it's easy to look at this because what I can do is because I have W measurement. I have this measurement. I do have this measurement. The easiest way to do is I move this measurement, W measurement from left-hand side to right-hand side, become my U. That's what I did. If you look at the first equations, I move the W and WC, let's move this from this left-hand side to right-hand side, particularly with KC, because KC is my computer quantity, so this is the KC, minus KC. Then parenthesis W minus WC, so this become my input force. So that, now from here, this is the force I want to be replaced by the actuator. All right, let's look at this. I want to replace by actuator. To design a mimic system is easy if we do this way. Now for that case, we have M 0, 0 MC, and we have W double dot, WC double dot, plus, and we have a 0, 0, 0, 0 C, W, WC dot, plus K plus KC, 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 and KC, and W, WC equal to 0 and 0. So this is my TMB. This is my, okay. And how can I change TMB to become feedback? All right, that's my feedback. Then how can I do that? It's easy to do that. The feedback is, look at the first equation, M W double dot plus, then I have a K加 KC here times W plus KC time WC equal to 0. And I can rewrite this equation become M W double dot plus KW equal to minus KC parenthesis then W plus WC dot, right? No,
我用错了。下一张，我刚有用到。
Okay, let me write this. No. Yeah. All right. So this minus here. This minus here. So this one here is equal to minus KC. Then W minus WC, and this is my U. So the feedback, this is my original system. I cannot do anything. But now this is the part, and this is from measurement. And this is from computer. All right, this is computed by the computer. All right, and this is also given by computer. And this U, after that, this U given by actuator. Right? Agree? Any questions? So the easy to design a virtual passive system is just write out your passive TMD, and then from your TMD, you move some of the terms to the right-hand side, and the term, then this right-hand side, this term will be all computed by computer. And the second one is the MC WC double dot plus CWC dot plus KCWC equal to KCW. All right, and this equation will be integrated by computer. And again, this W is for measurement. All right. So, that's you understand now the whole process. The process to design a feedback system, the process is easy. You write a TMD, the system you want to mimic, and then from that system, you move some of the term from right-hand side, from left-hand side to right-hand side. That right-hand side will be provided by your actuator, and also computer from your computer, and also from your measurement. This second equation is all computed by computer, but they do need the measurement. Make sense? You want to design a controller. That's the way to do it. You need to focus on the mimic system first. And this approach, you can generalize for a multiple degree of freedoms. And this is on a single degree freedoms. You can generalize. This become 2 degree freedoms, 3 degree freedoms. And the same thing, this one can be 2 degree freedom, 3 degree freedom, and 4 degree freedoms. Particularly this one is integrated by computer. You can have as many degree freedom as you want. All right. If your system has more than 1 degree freedoms, maybe your system like 101, maybe 100 degree freedoms, then your this feedback dynamics, they have to be more than just 1 degree freedom. All right. Any question about this? Any problem? Yeah, this is integrated by computer. W. You need to integrate this equation to get W. Integrate this to integrate by computer to estimate WC. Right? Whenever you get a measurement, give it to the computer integrates this, and then will give you WC. When you receive any new measurement come in, they integrate. Any new measurement come in, integrate. All right? Any questions?
Just a little.
This one?
No, that's equation. I think not the minus. Just a little mistake. In the first feedback,
the feedback is supposed to be minus? This one?
One step, yeah. Try to be minus case.
Oh, okay.
No,
This one. Thank you. Good. Yeah, that's true. All right. So that one, if you write the first equation, then it can become this. And so you replace part of it, the passive system, you replace part of it by the active system. So that's active system, that from active system. And this is passive. Right? So you simply replace all the passive devices by the active devices. That's all. The advantage of this one is the MC, you can change MC anytime you want. You can change zeta C anytime you want. You change theta C, KC anytime you want. This system, always stable system, just like this. It's always stable system. When you change MC, zeta C or KC, you change the performance. You perform maybe better with a different MC, KC, or zeta C. So the MC, zeta C, or KC, you can change any positive value. It has to be positive. Any positive values. The whole system, this system will be always stable. But the performance will be different. For example, you change this MC, all positive, change zeta C, KC. This, you change this these numbers, they will change what? They will change the system eigenvalues. They will change the system, the whole system eigenvalues. The system eigenvalue means you are changing the performance. So in your homework 5B, I ask you to change some of the number, change like some of this number, so that you get 5% damping. That's what it means. In passive system, you cannot change this, you cannot change that, you cannot change that. Like in TNT in the 101, this is fixed, this is fixed, this is fixed. Right? Now, when you implemented the TMD by feedback, and then you are allowed to change that, you are allowed to change that, not allowed to change that. For example, earthquake yesterday, in the middle of earthquake, you say, oh, performance is not good. You can quickly change that, make performance better. Understand? They're always stable. So this doesn't matter what, you change those, won't change the stabilities, but they will change the performance. Now, make sense now? Any more questions? So this is easier. Or you go home and do the homework. Maybe that will help you. Okay, it will help you to do that. And we know that as long as this is positive definite, this is positive definite, this is positive definite, they will be stable. And this is positive definite. If and only if KC larger than 0, K larger than 0. So as long as you are all MC, zeta C, and KC all larger than 0, then the closed loop system is always stable. A different value will have a different eigenvalue. A different eigenvalue means a different performance. Any questions now? No? No more? Okay.
How to calculate system eigenvalue?
For system eigenvalue, this is easy. You can we are the okay. Let me write it down. Okay, how to calculate system eigenvalues. All right. That's supposed to be my next chapters. And I just show you how. System eigenvalue. Assume this is the M. This is my my X double dot plus this is my Z and this is my X dot plus my K. This is a matrix. This is my X equal to 0, equal to 0, 0. Okay. This is all 2 by 2. and this 2 by 1, and this 2 by 2, and this 2 by 1, this 2 by 2, and this 2 by 1. But it can be any number. All right. The first step is now you move inverse x dot cross m inverse k x equal to 0. Oh, let me just say 0. Okay, it's supposed to be 0. We need a new pen. All right. Now, what we can do is I can say, okay, this is my zero dots and double dot equal to 0. This 2 by 2, 0. I, a 2 by 2. And this is minus m inverse k. This is minus m inverse j equal to x dot. Right? And this 0, 2 by 2 equal to 0, 0, 0, 0. I 2 by 2 equal to 1, 0, 0, 1. No ink. Any problem? I write this in terms that this x dot, 0 by 0 times x, is I by y, I 1, 2 by 2 times x dot, so that's x dot equal to x dot. Right? So this x double dot dot x double dot minus m inverse k, then times x, and minus m inverse z times x dot. Right? Any problem? The eigenvalue of this will be eigenvalue of the system. So this is the system eigenvalue in there. And each one is all these are matrix. This is only one way to do it. This is not only way. There are many other ways to do it. Any question? This is we call second order differential equation. This is first order differential equations. This is second order ODE. This is first order ODE. Right? Agree? Oh, this is from your engineering mathematics. How can you solve a second order matrix equations? It's just converted to the first order. And that's the way you solve it. Any questions? You have to check it if they can see it. I'm sure they can. The PC can see it. I think. Okay. Clear enough? Yeah. Any questions? All right, let's just think about it. How about that? Let us take 10 minutes break.
问问看这个，
就在密。
这个题他给的设计是一个重复的题，我怎么问？